Hello everyone, I'm Zhao from Nanjing University of China. I'm very glad to be here to report my research about D2D-based multi-relay assisted computation offloading in edge computing network. The outline consists of 5 parts. The first point discusses the background about my research. The second introduces the motivation of our method. The third concerns about the proposed D2D-based multi-relay assisted computation offloading method. Last but not least, there would be an experimental evaluation for our method. First, edge computing is proposed to remedy the shortcomings of the existing computing model. It puts computing and storage resources at the edge of the network near mobile users, which greatly reduces network latency and the consumption of computing and bandwidth resources in the remote cloud. It is seen as a supplement to cloud computing. D2D communication refers to a communication technology in which neighboring terminals can transmit data through sub-links within a short range without forwarding through the base station. Mobile devices in the blind area can obtain edge services with the help of the relays. The deployment of edge servers is still in its infancy. There would be some service in a blind area. By establishing a direct network connection between devices, D2D technology can help mobile devices and relays in the blind area to establish a D2D transmission link and obtain edge service. However, the existing method usually select single relay to transmit text and seldom consider the sensitivity of the processing delay for compute-intensive tasks. When the available bandwidth of a single relay is not enough to complete the data transmission in a limited time, it will cause a large network delay at the application end, which seriously affects the quality of user experience. So it is necessary to select multiple relays and the most reasonable computing type to be offloaded to the edge server for processing, so as to minimize the energy consumption of mobile devices and test execution time. In D2D computation offloading supporting compute-intensive tasks, the target device can select multiple relays to assist it in transmitting text data. In the process of assisting the target device to transmit data, the relays not only provide bandwidth resources but also consume the energy of target devices in the local. The compute-intensive text to be processed in the target device is recorded as MI, and we use alpha I to represent the proportion of text MI that is offloaded to the edge server. When text MI arrives, the target device's calculation backlog QI can be calculated. In the edge computing network, each base station is equipped with an edge server. Mobile devices need to go through the base station to access the edge server. And the time of a test MI executed on the edge server can be calculated. When relay J is used to transmit test MI, the transmission rate of relay J is Sj. The time for text transmission can be calculated when the target device offloads the text, and can be calculated. As a relay, mobile devices not only occupy bandwidth resources but also consume power. Therefore, in order to encourage more mobile devices to join the transmission process, the incentive model is considered for the transmission of relays. There is also a payment for the usage of edge servers. The cost for renting the computing resources is EE. And during the offloading, the relay can benefit from the transmission, can be calculated ER. And the overall cost for test processing is ER plus EC, ER, EE. In computation offloading, the test MI in the target devices to be processed executes in parallel locally and at the edge. Therefore, the test compilation time can be calculated. Ti is equal to the max of TIE plus TIT and the TIL. And the local energy consumption for MI is EC. The target device offloading utility for test MI is UI. And the optimization problems is the maximize the UI. When the target device is in the blind area, it needs to establish a D2D connection with the relay that can access the edge server to obtain the service of the edge server. Therefore, the target device needs to first confirm whether it is in the blind area, that is, whether it is within the service coverage of the edge server. This paper considers the case of edge server damage or downtime. In this case, although the mobile device can connect with the base station, the edge server equipped with the base station is difficult to provide external services. Algorithm 1 gives the specific process. It outputs the relay information, omega. Based on the strategy of transmission delay minimization, the data location DIG of each relay can be obtained, but also need to get the final relay site. Algorithm 2 gives a Gradebased iterative strategy. The Gradebased iterative strategy will include multiple iterations. In each iteration, the algorithm will first calculate the utility increase that each device in the set of to be selected relay devices can bring. After that, the algorithm will find the mobile devices with the smart lift utility improvement and remove it from the set of candidate relay devices. Algorithm 3 gives the steps of selecting a relay site. The relay site selection algorithm allocates the transmission data intending to minimize the transmission time, and then selects the relay site based on the utility value. Initially, the algorithm takes the whole set of relays to be selected as the set of relays to calculate the transmission data allocation corresponding to the minimum transmission time. After that, the algorithm will remove the mobile devices with the lift utility improvement at the in the set of relays to be selected in a graded way every iteration and calculate again until the site is empty. Finally, the target device selects the site with the largest utility values as the relay site. The construction method of candidate relay site is given in the previous. In this way, the target device can get the relay site DR, as well as the transmission data amount DI allocated by each relay. Considering the intensive deployment of edge servers, relays may be in the server coverage of multiple edge servers at each time. At the same time, therefore, the target device also needs to determine the proportion of data uploaded to the edge server. Alpha I and edge server K. Algorithm 4 will traverse the relay partition site, and each time it will select the current local optimal solution based on maximum uh, utility value, and then obtain the global optimal strategy omega. The strategy includes taxonomized offloading ratio alpha final, relay site D final, based based a base station K final. We select the Australian base station distribution dataset, which is derived from the radio communication license dataset issued by the Australian Communication and Media Authority. The text data transmission time and expected time are set like this. And the experiment uses the following indicators to evaluate the performance of the three methods. First is the proportion of tasks completed before the expected completion time. And second is the energy consumption of mobile devices accounts for the proportion of local execution energy consumption. We compare our method with the following two methods. First is the RSRO. It will randomly select a device from the set of relays as the relay. The target device will determine the offloading ratio according to the strategy of maximizing utility value. And the second is the GSRO. It will sort the devices and select the device with the highest transmission rate as the relay. The target device will determine the offloading ratio according to the strategy of minimizing execution time. We first change the expected completion time. Figure A shows the number of tasks completed before the expected completion time of the user. With the increasing expected completion time, the number of tasks that our method has completed is always the most. Figure B shows the ratio of energy consumption of considering to unconsidering computation offloading. The energy consumed by local devices using different methods if not related to the expected time change of test users, but the energy consumption of our method is always the lowest of the three methods. As can be seen from figure A and B, the performance of our method is always better than that other two methods, because a single relay may not be able to complete test processing before the user expected completion time. Then we change the number of relays to be selected from 2 to 20. Figure A shows that the proportion of completion tests before the expected completion time. With the increasing number of relays to be selected, the number of tests completed before the expected completion time with our method is gradually increasing. However, the number of tests completed by the other two methods before the expected completion time has little change. The performance of method is always the best. Figure B shows the ratio of energy consumption of considering to unconsidering computation offloading. The energy consumption of our method is decreasing and remains the lowest at all times, but the energy consumption of the other two methods is unchanged. This is because the other two methods can only select the one relay. So the improvement of the number of relays will not improve the performance of the algorithm. However, our method can use multiple relays for parallel data transmission at the same time, which greatly improves improve the performance of compute-intensive tasks. Finally, we test the impact of the number of available edge servers. Figure A shows the completion time before the expected completion time. As the number of available edge servers is decreasing, the performance of three methods are decreasing, and the number of tasks completed before the expected completion time decreases, but the performance of our method is always the best. Figure B shows the ratio of energy consumption of considering to unconsidering computation offloading. With the decrease of the number of available edge servers, the energy consumption of three methods for target devices is increasing, but the energy consumption of our method is always the lowest among the three methods. The reason for the above phenomenon is that with the decrease of the number of available edge servers, the single relay-assisted offloading method is difficult to support more compute-intensive tasks, which our method with multi-relay strategy can. Moreover, the continuous reduction of the number of available edge servers makes the target devices put more tasks on the local execution, so the energy consumption of mobile devices will continue to increase. However, our method is still superior to the other two methods. That's all. Thank you for your listening. Any question, please contact with us. The email is here. Thank you.